Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be talking about another algorithm design technique. So just to give you a heads up for where we've been so far. So far we talked about greedy algorithms. We also talked about divide and conquer algorithms. And in addition, we also talked about, I asked you to read a little bit about this concept called backtracking. Now, there's a whole bunch of these different techniques, and I want to kind of jump and kind of take a couple bits and pieces here or there, just to kind of stitch together an idea where we're going today. So last day we talked about divide and conquer. And in this idea, what we did was we take the problem, we subdivide it into smaller problems, and the goal is that if we make them small enough, we can easily solve those problems. And then the idea is that we could take those solutions, we could combine them together to solve the overall problem instance. This is in contrast to something like backtracking, where you think of the process of doing it as a big decision tree even of sorts, where I have stages that I make decisions. So one thing I would like to do today is I would like to take this idea of having my solutions done in stages, kind of like the greedy algorithms, by the way. Remember the greedy algorithm? I produce a partial solution as I go along, and I make sure it's a feasible solution. Same idea. It's the same idea. I would like to have this, but also I would like to try to find some much more clever way than, say, brute force or something else like that, to try to come up with a way to solve a problem where I could combine those problem solutions just like a divide and conquer. But here's the catch. I want to do it smarter than that. So not just simply just saying, hey, look, I'm going to just do a whole lot of recursion and let's see what happens. I don't want to just do that. I want to do something smarter. So today I'm going to introduce an idea that first this will seem kind of like, oh yeah, that seems kind of obvious, but it's actually rather ingenious at its heart. So I'm hoping to convince you of both of these observations. So first, before anything, I just want to give you a flavor for what dynamic programming is about. And then we'll do an example, and then we'll kind of tackle an actual problem. So dynamic programming is simply a method for solving problems by combining solutions of subproblems. So that should sound familiar to you from divide and conquer the other day. But the idea is that the dynamic programming is suitable for when a problem has many overlapping subproblems. So we're going to see what that means. In fact, we've encountered this phenomenon before. For example, when we talked about the single source shortest path problem, do you remember how I told you that if I have a shortest path tree, that if I look at any one path in that shortest path tree, that in itself was also a shortest path, right? So if I decompose the shortest path tree, I can also get shortest paths. The same idea still applies there. It's actually because in that problem as well, you could actually use dynamic programming. But there's only very specific problems where you can use dynamic programming. And we're going to see the criteria for doing and conducting dynamic programming under very specific circumstances that guarantee an optimal solution. So we're looking at optimization problems. So just keep in mind that we're going to try to combine solutions, but at the same time, we want to make sure we take advantage of the fact that many of these subproblems, they look very similar to each other. So there's going to be two main ideas that comprise dynamic programming. The first is the so-called principle of optimality. I'll give you an idea what that is in a little bit. And the second one is memoization. So just to give you a flavor, just before we get a little bit ahead of ourselves, I want to give you an idea where this came from, this idea of dynamic programming. So as I described it as, I thought about it, we think about it more like a multiple stage decision process. So back in the 1950s, a fellow named Richard Bellman, we actually came across this name actually earlier on. Do you recall when I was talking about the single source shortest path problem, I mentioned that there's this algorithm called Bellman-Ford? The Bellman in that algorithm, as that name is, that's the same Bellman I'm talking about here. The story goes that, that for the Rand Corporation, they were doing some research specifically for the Air Force at that time. And at that time, at least this is how the story goes that Bellman has, is that mathematical research was very difficult to get research money for at that time. Typical of doing research, sometimes if you're in an avenue where it's not terribly popular to do research in that area, what Bellman would try to do, because he's seen the intrinsic importance of solving these so-called multiple stage decision processes, what Bellman did is he gave this a name, akin to something like some of the other terms that would be rather popular at that time. For example, I'm not sure if anybody's ever heard of the concept of linear programming. Now, the name programming here isn't about like computer programming in the sense of, oh, we're writing up a computer program. It's for planning. So it's a term especially that was popular in that period, especially from the military. So linear programming was quite popular at that time. But at the same time also, there was a very natural idea for planning, and you can think of it like a multiple decision process in terms of planning. And this dynamic sense has to do with how the planning is done. It's not a static thing, it's a dynamic thing. Hence why it's called dynamic programming. That's where the term comes from. So if you're wondering where the name came from, that's generally the idea. It's mostly because that Bellman needed to find a way to coin the phrase that he wanted to explore. He wanted to look at these dynamic decision processes back in the day. So we'll talk more about the principle of optimality, this is what Bellman was working on originally. And let's talk about this memoization. Let's start with the second part first. So let's talk about the concept of memoizing. So you're going to find that this is an idea that isn't just helpful for dynamic programming. You can use this idea in many different settings. So this is why I like to introduce it separate, so that you have a flavor for how you could use it in other settings, because it is an optimization technique. So especially if you're implementing recursive algorithms, memoization is your best friend. So here's the idea. To memoize simply means to store a solution to a subproblem, and so whenever you say solve that problem, instead of resolving it over and over again, you store that away so that when you need it, you just simply look it up. So you might ask, Dan, what is this word? Like, it looks like you wrote down memorization. That I can assure you it's not a typo. Memoization is a combination of two words. Memo and memorization, as you might suggest. So it's the combination of these two words, and it's like that for a reason. So you can think of it like this. So for those that have been in a workplace, you may know of the concept of a memo, or you may just know generally of the idea of a memo. So in a workplace, for example, you may run into a situation that needs to be resolved, a problem. And sometimes it has to be the case that management finds out, okay, we have this situation. How can we relay that information to other people? Well, they might draft this in a memo and put it on a bulletin board. And they'll say, hey, look, so usually when the workers come in, they look at the bulletin board to see if there's anything there. Or say if this is a digital memo, it might be sent out in that morning. So you could think of it like that. So it's a very natural idea if you think about it, rather than recomputing my answer every single time, as in, say, for example, I'm a worker and every time I keep running to the same exact situation, instead of not knowing what to do and every time I handle it each time, I just simply appeal to the memo. The memo told me to do this thing, and I just relay it to that. So just for an example of what I mean by this, say, for example, we talked about the idea of just, say, computing a sub-solution. What we're going to do is we're going to use this idea to build up answers in dynamic programming. But just to give you a flavor for what I mean and why this might be valuable is, say for example, I asked you what 2 plus 2 is. And I'm not going to ask you what 2 plus 2 is. I hope you know the answer for this. I most certainly believe you do. But you might tell me, okay, the answer is 4. So what I can do is I can put that answer right there. So whenever somebody asks me, hey Dan, what's 2 plus 2? I could point and say, hey, look, there's the answer. I don't have to do the calculation in my head. I just have to use my mechanical ability to pick up my arm and point at it, right? So that's all. So this is the idea for memoization. It's just, if ever I need to recompute something, instead of recomputing it myself, I just appeal to my memory. So my memory in this case, a memo. So what this will be on the computer is a table that you can look up. So you just think of it as a lookup table. So you might ask, Dan, what does this have to do with anything interesting? Like 2 plus 2, that's not very interesting. I think it kind of is. But suppose that I did store several of these. Suppose I had several answers, and say I'm coming along like an inspector trying to see what exactly are the decision processes going on at this workplace. What I could do is I could go through the memos and see what exactly is being done. So I look at each one of them. So here's an idea. Suppose that I have some of these memos that tell me what to do in different circumstances. So what if I told you that there's a nice way to take these memos that I post up and I could combine them to find out what I should do next? And that's actually going to be what's at the heart of dynamic programming. So just first, are there any questions about the idea of memoizing? All it is just you store away the answer to some subproblem. So if you ever run into it again, you could just point your finger at it. So this would typically be implemented as some data structure. In this case, you could just think of it as a table. So you can think of it as just an array, but you may have a more sophisticated data structure like a dictionary or something like that. But here's the idea of memoization in its heart. So as an optimization technique for programming, so let's see, would 1 plus 2 plus 2 plus 1 be stored in the table as the same thing? Well, that's an interesting thing. We're going to see how this plays out in dynamic programming. But most certainly, you would organize your table in a way that makes sense for what you're trying to do with it. So it's not going to be like there's one universal way for me to accomplish this. You got to remember, dynamic programming, as we're going to see it later, is going to be this much broader class of ways of solving the problem, but each one is unique to its problem. So anyways, as an optimization technique for programming's sake, if you're wondering what I mean by memoization, so you can imagine you have a recursive algorithm, like a divide and conquer algorithm. And you have this top-down process, because you can think of divide and conquer as a naturally top-down way of solving a problem. So here's an idea. What if you have it where you store away in this table all of your subproblems? Whenever you encounter one of them, you solve it. And if you run into it again, to reduce having to redo all of that work again, which is possible in recursion, you just simply appeal to the table and you find out the answer directly by using this bit of memory. This is a typical way in practice for cutting down the time necessary to do a computation like that. Is that kind of neat? So just using a bit of memory can save you a lot of time, as we're going to see in our example shortly. So in dynamic programming, as I mentioned, imagine you have all of your answers in a way that makes sense for the formulation that you're going to have. This is going to be based on a recurrence relation. We're going to have a way to tabulate, so take these answers I have and combine them such that I can build up to a solution. So divide and conquer is a very natural top-down way of solving a problem. Dynamic programming is a very naturally bottom-up process. So I'm going to talk about how we could solve problems in a bottom-up manner. So at first this sounds a little bit strange because you heard me say recurrence relation and you heard me say these other things. So it sounds really kind of strange at first, right? So the whole idea is I'm going to show you how you can combine answers to problems to solve the overall larger problem. And at the heart of it is this ability to tabulate the answers by combining them. Just like if I had my memo here and I had several of these, I could find out what I might have to do next. So are there any questions before we get to our example? So I must stress I have not yet defined what the principle of optimality is, or at least given you an idea of what that is. This is a key part for dynamic programming. If you do not have the principle of optimality, you cannot use dynamic programming to solve the problem to optimality. So I haven't yet defined that quite yet. Or at least given us the idea for it. So if we're okay, let's go to our first example. I thought we'd start with something a little bit simpler, just to give you the basic idea. So let's start with something a bit gentler. And I'm sure you may or may not have seen this as an example before. So I thought we would start with something basic. So I thought we'd talk about computing the nth Fibonacci number. So you may or may not have seen how you could compute this recursively using a recursive algorithm. So I want to talk about this. So we're going to talk about computing the nth Fibonacci number. So I want to first give you the recursive definition of a Fibonacci number. So if I give you an arbitrary n that I want to compute, the way I determine that is from the previous Fibonacci number and then the one that's just before that one, and I add those two results together. But the first two Fibonacci numbers, at least in the way I'm going to define it here, is Fib1 is 1 and Fib2 is 1. So for example, if I wanted to compute what Fib of 3 is, Fib of 3 is just simply Fib of 2 plus Fib of 1, which we know this is 1 and that's 1, so that means that the answer is 2, right? And you can keep repeating this, doing this process over and over again. So for example, you can have it being where it's 1, 1, 2, 3, 5, 8, and so on. It's a very classic sequence of numbers. It's interesting in its own right. So what I'm going to do is I'm going to translate this recursive definition into a recursive algorithm, and this is what I end up getting right here. So first, before we proceed, are there any questions about my pseudocode here? I think this is a rather natural recursive algorithm for Fibonacci. But if you have any questions, don't hesitate to stop me before I get mad with power. I kid, of course. Okay, so let's talk about this. So if you were to analyze this algorithm, you'll notice there's a couple of interesting things going on here. So using the techniques we've talked about in this class, you'll notice that, okay, so this takes some constant number of operations. However, notice that there's two recursive calls here. So if I ignore all the recursion, you know that this takes some constant number of operations, right? Overall, if I ignore the recursion, right? So if I ignore all the recursion, this is some constant number of operations. So this is, of course, big O of 1 ignoring the recursion, right? But once you introduce it, this turns into a very interesting beast. So for those that have seen this algorithm before, you might have a flavor for what's going to happen based on how we would adapt this into a recurrence relation. So, for example, you'll notice that we have two recursive calls, one where one gets smaller than the other one gets smaller by 2. So I have a question for you. If you know that, if you were to imagine this like a recursion tree, where first I do some constant number of operations, and then I do two recursive calls, each one where it's just the input 1 less, right? And then the other one is for 2 less. You're going to end up with something that looks something like this, where it spawns 2 children. Then one of these sides is going to at least spawn 2 children. And then this one's going to spawn potentially 2 more children, depending on what value of n it is. And it spawns 2 children. Then that might spawn 2 children. But notice here that every time it's just doubling, right? So if I were to bound how deep this tree can go, does anybody have any ideas of how deep this tree might be? You can even just state it to me in terms of big O. How deep can this tree be? This recursion tree. How deep is that going to be? If every single time, you know, at least one of these branches is going to split into 2 every single time. So it's going to be doubling every single time. But the thing is, the value of the input always goes down by at least 1. So remember here it's n, then say n minus 1, then n minus 2, then n minus 3. So it's not quite logarithmic. It's not logarithmic. Eventually this is going to go down till eventually when it's either 2 or 1, right? So eventually it's going to be where you're going to hit leaf nodes down here, but some of these may actually hit the leaf nodes much earlier on. But if you're thinking about this from a recursion tree standpoint, you can just simply determine what the overall height of this recursion tree is, and determine how much work is happening at each level at most. So if you actually sum across each one of the levels, I want you to notice that at this level, the amount of work is at most 1. Here it's at most 2. Then here it's at most 4. And then here it would be at most 8, right? Then next it would be at most 16. But notice it's doubling at most. Keep in mind it might be actually smaller on one side of this tree. But the point is every time the input goes down by at least 1 and it just doubles like this. Does anybody see, if I were to use the recursion tree method, what a nice big O result might be here? So every time it's just doubling, and can you see what the height is? So notice that each time it looks like it's being at most whatever the doubling of the previous level. So yeah, it's going to be doubling every single time, and you know the height of this is going to be, it's big O of n, right? So you know it's going to be definitely something linear, but every time it's doubling, so if you sum over all of these, you're going to end up with something that looks like big O of 2 to the power of n. So its time complexity is big O of 2 to the power of n. That's really slow, right? That's really slow. That's like terrible, right? like you look at this, like this simple little formulation, you're looking at this like, okay, that's 2 to the power of n. This problem must be very difficult if even a very natural way of characterizing it might take this long. That's at least one way you might think about this problem. One thing I'll make a remark about is if you're much more careful with your analysis, which in the recursion tree method, you can be quite sloppy and still get a correct big O like this. I must note that this is a big O, not a big theta, because you could actually improve this so that it's big theta. If you were to be tighter with your analysis, you'll end up with big theta of the golden ratio to the power of n, where the golden ratio is where, if you don't know the golden ratio is 1 plus the square root of 5 over 2. Which, if you're not sure what that is offhand, that's just something like 1.618. It's something about that. So you'll notice right away, if you actually were to be optimistic about how this tree is doing the splitting process, it sits somewhere in between 2 to the power of n over 2 and 2 to the power of n. So that's why it's somewhere kind of sandwiched in between the two. So you might ask, okay, Dan, what's the problem here? Does anybody see anything interesting that's going on yet? I will spell it out in a moment, but does anybody see anything kind of odd that maybe I'm doing when I carry out this algorithm? Is there anything I could be doing better? Any ideas at all? I'm happy to take any suggestions. There's got to be some, like, this doesn't seem like a very difficult problem. So why is this taking so dang long? like this is exponential time. If you were trying to implement this for a large n, that's going to take a while, right? So any suggestions? So if there aren't quite any suggestions, I have one picture I want to draw for you just to really spell out what's going on here. Okay, so I got one suggestion. Find a closed form formula for the nth Fibonacci term. Yep, you can do that. In fact, there does exist an actual formula for this. That is one way you could do it. That is indeed one suggestion you can make, is you can actually compute what the nth Fibonacci number is using an analytical closed form. That is something that we could do. I want to specifically focus on how I can speed up this algorithm. So that is a very good suggestion, by the way. But I want to show you what we could do to this algorithm to make it better. And better is not really an objective term. I should be a bit more precise. How to improve its time complexity based on some of the ideas we've talked about here. So I want to draw out a call tree just to give you a flavor for what's going on here. And hopefully you'll be able to point your finger right when you start seeing it, what's going on here that maybe, just maybe, sorry, I'm getting very excited. I'm taking the 4 down. I hope everybody will remember this. I'm just joking, of course. I might not. I'm just... Anyways, so let's take a look at an example here. So I'm going to say there's an issue. Now, that algorithm is indeed correct. It's just literally just using the definition of the Fibonacci number. So let's consider an example. Let's look at fib of 5. What happens when I do fib of 5? So when I call fib of 5, I'm going to look at its call tree. So I'm going to have fib of 5. You know that for fib of 5 to be computed, on that algorithm, I have to do fib of 4 and fib of 3, right? I have to call those two in the algorithm. So you know I'm going to require calling fib of 4. And I have to call fib of 3, right? Now, to call fib of 4, I have to do what? I have to compute fib of 3 and fib of 2, right? That's what the... So I have to do fib of 3 and fib of 2. But to do fib of 3, I have to do fib of 2 and fib of 1, right? Fib of 2 and fib of 1. Likewise, for fib of 3, I also have to do fib of 2 and fib of 1. That's what the algorithm will do. So when I go through all of the recursion, I'm just summarizing what all the invocations will be in the form of a tree. Now, do you see the problem yet? Is there anything you see here, if you're thinking and putting on, say, an optimization hat, that I am doing wrong, but Dan is being very silly? Yes, exactly. You see, there's a lot of duplicate work going on in here. So there's a lot of work I'm repeatedly doing over and over again, right? So notice that when I compute fib of 4, I do fib of 3 and fib of 2. Now fib of 3, if I were to compute this once, I could store that answer away in a table, or just think of it as an array. And whenever I compute fib of 3, I could just check if I already solved it first. If I solved it first already, I'll just invoke it. I'll just grab it. If I haven't done it yet, I better calculate it. So naturally, you can see that one big problem I have here in this tree is that there's a lot of redundant computation. So I'll say, let's see, there's a lot of redundant computation. I'm doing a lot of repeated work. There's a lot of redundant computation. So, indeed, you can use memoization. That's one way you could speed up this algorithm considerably. So you could see how, for example, just to give you kind of an idea what I mean by this, is you can imagine I have an array. Say, if I'm doing fib of 5 here, I could imagine I have 1, 2, 3, 4. Say if I have an array of length 4, for example, and when I compute fib of 5, each one of these entries, whenever I look in each position, if I want to get, say, fib of 3, it would be in this position. It'll be one less than whatever the number is. So imagine I started off at 0. That would be what fib of 1 is. So I know what fib of 1 is, and I know what fib of 2 is, right? So this is just fib of 1. And I know this is fib of 2, right? So if ever I need fib of 1 and fib of 2, I could just look in this array, right? So all I do is I take whatever the number is, I minus 1 to get its position in the array. So if I call this like array A, I could just simply just grab it out of the array, if it exists. I could presume that all of these are, say, 0 for now. So that would be, for example, one simple condition I can check to see if I've computed it yet or not. So I'm just giving you an idea of how I could do this with memoization. So if I were to doing fib 5, I'll recursively call fib 4 first, because that's the first of the 2 recursive calls. And then this one will do its first of its 2 recursive calls. So I'm at fib of 3. Well, fib of 3, well, I haven't computed fib of 3 in, right? So what I can always do is I can compute that. But since I don't have the answer for it, I'll just call fib of 3. So I do its 2 recursive calls. I get fib of 2 and fib of 1. I get its outcome, and I store it in here. So I just store it here. So that's what fib of 3 is. So if ever I need to know what fib of 3 is, just like when I was checking if 2 plus 2 is equal to 4, right? I can come back to it if ever I need to recalculate it. So now I have figured out what it is here, but now I have the other call. I know that my position in the array, I checked the first position 1 here. It's not the first position, it's position 1. I checked there, I already have it, right? So I just give back 1. I can add these two together. So I get 1 plus 2, and I get 3. And that gives me fib of 4. Now, this is where it gets fun. So I have fib of 4. So I finished that one. Now I do the second recursive call on fib of 3, and I already have fib of 3, so on the fib of 3, I just simply look in my array, do I have a 0 here or not? And fortunately for us, there is not a 0 there. It has 2, so I just give back 2. So that means that I don't have to do any of this. In fact, when I did this whole process, I didn't have to go through much of this, really, because all of these are base cases, but you can imagine very quickly that if this was a very big tree, how much I would actually be eliminating is actually quite a bit. It grows exponentially, by the way. So you can see that when I compute fib 5, my apologies, I'm just getting very excited here. I could just easily compute that, and I get 5. So, are there any questions about what I did here? So this is just me giving you an idea of memoization with recursion. So this is how you could speed up a recursive algorithm. So this is one optimization technique you can use to speed up calculations, is you just use a bit of memory to make it faster. So we're going to use memory to be our best friend here. So now I want to show you something interesting that we actually did here. Did you notice the order I was calculating them in? I started here, and then I calculated 2, then I calculated 3, and then I calculated this 5 out, right? Did you notice I swept left to right? Did anybody notice that? That's rather interesting, right? Now, it might tell you something very obvious that we could be doing instead of all of this work. Does anybody have any ideas of a much more natural way of doing this so I don't have to do all that recursion? Yeah, you just start over here, and remember, I already know these two values, so I could just fill in this array from left to right. I don't have to go through all this recursion. Does everybody see that? Isn't that very subtle and interesting? So this brings me to how I can do and solve this problem with dynamic programming. So this is me using memoization, and you can think of what we just did here as what some people refer to as top-down dynamic programming. I refer to it as memoization. So let me give you how I could do this and approach this with dynamic programming. Here is a basic dynamic programming algorithm for fib of n. So let's talk about this. So you're going to see that this is really going to mesh two ideas together. So we've seen how we can use the lookup table, but now I'm just going to use the lookup table to build the answer. So as opposed to just having it where I use it as just a facility to look up my answers if I need to recalculate them, I could just simply build them up. So why? Because I know how it's actually being carried out. So here's my dynamic programming algorithm I'll present you. So algorithm, let's talk about fib dp of n. So this is going to be the dynamic programming algorithm. So same input and output as before. So it's a positive integer n, and the output is going to be the nth Fibonacci number. So it's going to be the nth Fibonacci number. So here we go. I'm going to first start by creating an empty array. So it's just going to consist just like what I had here. So I'm just going to start off. I'll call this array fib, all lowercase like this. So create a new integer array of length n. So note that it's going to be indexed as this, 0 to n minus 1. Don't mind me. I'm just going to get some water here. Okay, here we go. So I got my array. So I'm just going to create this array at first. And now all I'm going to do is just apply what we just talked about for our previous algorithm. But I'm just going to use the observation I made here. Well, what we did together was observe how we can build up this table using previous calculations. So we're going to have a for loop. For I is assigned 1 to n. We're going to do the following. So I must stress that you can make this even simpler by just assigning the first two positions to be 1 and then starting immediately after that the first two positions. You can also rewrite it like that. I'm just going to put it all together just to emphasize the recursive definition just embedded inside of this algorithm. So if I is less than or equal to 2, then I'm just going to assign fib of I minus 1 to be 1. So I'm just going to start off by just putting in my base cases. Just fill them into those first two spots. Otherwise, I'm just going to have it where I just apply my recursive definition. So I'm going to have fib of I minus 1 is going to be assigned, and I'm going to write it this way to make it a little easier for you to see what I'm up to. But you can easily rewrite this to be a little simpler. Fib of I minus 1 plus fib of I minus 1 minus 2. All in the square brackets. I sort of ran out of space there. So fib of I minus 1 or fib of I minus 2 plus fib of I minus 1 minus 2, or fib of I minus 3. So now all I have to do now is I just close up my for loop and I just access the last position of the array. So I just return fib of n minus 1, and we're done. Boom. That's it. That's it. So this is my dynamic programming version of computing the nth Fibonacci number. So you might naturally ask, and one thing I do actually want to make a remark about is that when we have an array with only one dimension, so it's a one-dimensional array, we sometimes call this one-dimensional dynamic programming. Just to make sure it's clear, like when we build a table, you may have several dimensions for your table. Usually it's the case that it's only a two-dimensional array. And the indexing on this table might be literally indexed by numbers, or may actually be indexed by entities like sets, which you'll be encoding as numbers. So we'll be seeing examples where it's actually indexed by numbers, but in some more complicated examples out there in the literature, it may actually be where like each position might actually be indexed by a set that can be encoded as a number. So that being said, I have a question for you. Question. What is the time complexity of this algorithm instead? So what's the time complexity here? So before I had 2 to the power of n, or if I want to be a bit more precise, big theta of the golden ratio to the power of n. What's happening here? Well, you go through this loop n times, right? So we know we make an array of length n. So we know this is going to take linear time to construct this array. Then I have to go through each position in the array. Then I just return the last position. So if you're thinking about something linear, that's pretty intuitive, right? So you might look at this and you say, okay, well, that means the time complexity here, well, that has to be big theta of n in the worst case. In fact, there's not really cases here. It's really straightforward, right? It doesn't matter which case it is. It's just going to always do this. So that means very natural idea. What I'm going to do is I'm just going to illustrate now the ideas of dynamic programming. So we actually seen and manifested at least 2 of them. So the main 2 ones that I talked about. So notice that Fibonacci, every term of the Fibonacci sequence can be derived by other numbers that are results of the Fibonacci number, right? That's from its recursive definition. So we use the structure of how we can organize those, and when we tabulate them in that table, I can combine those answers to figure out what the overall answer is. So rather than having to recalculate it over and over again, like in my call tree here, I don't have to do all that work. I use the structure of what the subproblems give me, and I combine those answers, so I get sub-solutions that give me the overall solution. So you got to think about it now as I have a subproblem, each of my subproblems have a sub-solution, and I can take those sub-solutions, I can combine them just like I had my memo on the board. If I have several of those, if I know how to reorganize them to get the true process that I need to carry out, that's all I have to do, believe it or not. So you've actually just seen how dynamic programming can be used. And one of the more simpler ideas that you get from this, that you should kind of notice right away, is that we use memory. So one main idea is to use memory to reduce the redundant computations. So that's the first big thing I want you to notice, is that I used this memory, this array, to organize my answers, but notice I used the recursive definition of Fibonacci here, but I used the table to formulate and combine my answers. Does everybody see that? So I didn't have to do it like a cold turkey every single time. I'm not going to cook up a turkey every step. If somebody else knows how to cook the turkey and has it all ready for me, I'm not going to cook a new turkey whenever I'm hungry for a turkey. Don't ask me why I'm just suddenly hungry for turkey. That's just a whole other discussion altogether. But the point is that I don't have to do all that work over and over again every time. I use the memory to store those answers. And because I know the recursive definition of the Fibonacci sequence, I know how they're organized in this array or table. So I'm going to give you a very important phrase that I really want you to take from this. And this is a very valuable lesson. I think I may have said this to you before, but I want to give it to you as a tip. So I'm going to go over here and I want to write it down for you, because this is one of those things that, even if it's not applicable to dynamic programming, it's something that at the end of the day, I want you to remember, is that when you think about computing, we usually think about time, right? We think about how long things take to compute. Now, there was a time in the history of computing when storage was very, very expensive. Now, in these days, unless you really have a lot of data that you're working with, storage is much cheaper these days. So here's a tip. Just don't forget that we have storage. So you can reuse memory, right? We can reuse memory. You cannot reuse time. And I don't mean that in a weird kind of way where, oh, we can reschedule everything we're going to do. I'm not meaning that. I mean that the time we use for those computations, we can't get back. But I can use memory, like I can allocate an array. I can reuse that memory afterwards. So that's one of the intuitions I want to help you with when we think about dynamic programming, is that we can use that storage to speed up our computations by removing those redundant computations. So this is going to be very helpful for us when we study tougher problems. So problems that the best known algorithms we have for them take exponential time. So whereas we might have to do a little bit less of a less charitable way of approaching to solve the problem, we might use a lot more memory. If I'm a lot more careful about how I organize that data when I use my memory, I could probably get away with cutting back a little bit, or at least I can organize it in a way that's easier for me to implement, but also deliver an optimal answer. assuming that the problem satisfies so-called the principle of optimality, which I want to describe now. So the first thing I need you to know about is in order to apply dynamic programming, to solve a problem. So remember, we're talking about optimization problems here. So that means that I want it so that the algorithm always produces optimal solutions. That's always give me the best answer. To solve a problem, the principle of optimality, which I'm going to lovingly contract into a cute acronym that I know almost nobody uses, but I like to use it because it's a lot less work on my hands, is the principle of optimality, or I'm going to make it as an acronym POO, must apply. That it makes everybody enjoy. Oh, Dad said poo. So let me describe what the principle of optimality is. So the principle of optimality is said to apply to a problem if an optimal solution to an instance, so we're talking about a problem instance, always contains optimal solutions to all sub-instances of that instance. I'll elaborate what I mean by that in a moment. To all sub-instances of that instance. I must stress that Bellman's original formulation of the principle of optimality is a lot more complicated than this. They would. Of that instance. In other words, a given problem has the following two properties: overlapping subproblems, and it also has what we call optimal substructure. We've actually seen examples of both of these before. Remember, as I said at the beginning of lecture, when I talked about, say, Dijkstra's algorithm, when we use Dijkstra's algorithm, we're exploiting the property that a shortest path tree consists of shortest path trees, where if I were to omit an edge, whatever's left there is still a shortest path tree, just without that one vertex in it. And it's a corresponding edge that gets me to that next shortest path. Likewise, this manifests in a lot of different optimization problems, but the shortest path problem is actually one of the original problems that Bellman was actually looking at when we looked at the so-called idea of the principle of optimality as the shortest path problem. It's not the only one, but it's definitely one of the classics. So you can actually take, for example, Dijkstra's algorithm. You know how we described Dijkstra's algorithm? We talked about it as a greedy algorithm. You can actually reformulate it as building a table, kind of like my previous example, except you'll have I believe it's a two-dimensional array. And what you would do is you would actually build it using a recursive notion of the shortest path based on our idea of edge relaxations. So believe it or not, you can actually represent, say, Dijkstra's algorithm as a dynamic programming algorithm. But I must stress that some of these different techniques actually overlap with each other based on the properties of the problem. It's not that you can so just to be very, very clear, just because you can design a greedy algorithm for one problem doesn't mean there exists a dynamic programming algorithm, and likewise, there might not be a divide and conquer algorithm. Remember, you always have to look at the given problem at hand and the properties it has. Dynamic programming has some fairly strong conditions, but greedy algorithms actually have a little bit stronger conditions that you have to be a bit careful about. Remember, we have the greedy choice property, for example, that every time I make a locally optimal choice, it leads to a globally optimal one. If a problem has nice properties like that, but it also has the ability to have only one single pathway of choices I can make, or if I ignore the ties, then a greedy algorithm will suffice, which is very nice because they're very simple to implement. But we're going to see that for a lot of problems, that isn't going to be how it works. So dynamic programming is a little bit more of a broader class of way if I can try to solve the problem, because it will be able to help and deal with those branchings of possible best answers. So let's talk about how we're going to design a dynamic programming algorithm. So I want to kind of give you an idea where we're going to go with this. So let's go back over here. Actually, before anything, are there any questions about the poo? So just if you're wondering what I mean by an instance always contains optimal solutions to all sub-instance, to all sub-instances. Sorry, I'm getting very excited here. So if I give you a given problem instance, and imagine it's consisting of a bunch of items. If I tell you that this is an optimal solution, what also has to be true is if I remove an item from this optimal solution, what will happen is whatever's left, if I create an instance, a sub-instance, that consists of all those items without my one item in it, that'll actually also be an optimal solution for that sub-instance. So you're going to see this actually in our first example. So our kind of more meaty example we're going to be doing for dynamic programming. I'll be giving you actually another example to read as well after we do this one example. So this is going to be kind of like the meatier example so you get the idea of how this works. So that when you look at the other example, you'll be like, okay, I see, this is what's happening. So I want to give you an idea for how we use this so-called principle of optimality. So remember, I told you that it gives you a way. So if I gave you, supposedly I had an optimal solution, you know that it decomposes into, if I removed an item or a part of that feasible solution, in this case an optimal solution, if I remove a part of it, it means that whatever's left will be an optimal solution for some sub-instance. So if you think about it like that, you can imagine it where, I imagine I have my sub-instances and I look at the smallest ones first. Think of it like a recursive or divide and conquer algorithm. Think of something like merge sort, for example. You know, in merge sort, you make all of your subarrays down all the way until they're all of length 1, and then you combine them all together by merging them successively, right? Well, in dynamic programming, what you can do is, if you have the principle of optimality, is you can imagine you start at the bottom. So instead of starting from the top doing this divide phase, you can imagine you're at the bottom of this thing. And you can actually solve each one of the smaller problems at the bottom. And what you could do is, once you have the answers for these, since you're tabulating them through building our table, you can use those answers, just like I had my memo, I can use those to combine them in a specific way to get the next largest set of optimal solutions to some sub-instance. So eventually, if I'm looking at my given problem instance, I can make these successive choices to construct bottom-up the answers. So you're going to see that it's almost like we're going backwards with our recursion. So we're starting at the bottom and working our way up to the answer, which would have been the initial recursive call. But we don't have to actually consider it at all from a recursive standpoint, just the way we derive it is recursively. So that's why I say that dynamic programming is a bottom-up process. So we're going to use this thing, this principle of optimality is key for doing this. So here's a strategy for designing dynamic programming algorithms. So one, of course, you have to establish that the principle of optimality does suffice for the problem. So make sure, of course, that the principle of optimality is satisfied. So this is something you typically sit down and prove. Now, our Fibonacci example is rather contrived because it's really straightforward. It's literally from the definition, right? But for some problems, it's not straightforward. It's not straightforward that it is. So once you know that the principle of optimality is satisfied, the first thing you'd probably want to do is establish a recursive property. Establish a recursive property that gives the optimal solution. I'm just going to switch my marker. I know I have to do this, but I'm looking at that. I'm like, I don't know. This could be better. Let's hope that this one's better. Let's see if we get lucky. Give the optimal. Oh, that's much better. Gives the optimal solution to any instance of the problem. Now, I'll give you a big tip. A big tip with number one. This comes from usually the proof. Usually, I'll approximately say that that the proof tells you this. So if you're wondering about, okay, where does this idea come from? The principle of optimality's proof typically spells out what you're supposed to do. We're going to see this with whatever time we have left. Yeah, we have enough time. When we see our example of proving the principle of optimality is satisfied for our problem, you'll see that it will actually give us an idea of the underlying structure of an optimal solution so that we can recursively describe it. So that's the first step usually, once you've determined that the principle of optimality holds. The second step typically is to compute the value. Compute the value of the optimum in a bottom-up fashion. I thought this marker would be better, but suddenly I was teased. In a bottom-up fashion. A bottom-up fashion. Then obviously once you have that, believe it or not, because you make a sequence of choices, and this is sort of the magic of dynamic programming. I wouldn't want to use the word magic. I use it more of in a loving, like endearing way. Is that it's very magical in the way that all the theory that underlies this actually comes together so you can actually figure out what the optimal solution is. So you can figure out what the value of it is, and to determine the value of the optimal, you have to combine potential subsolutions values. And every time you do this, you tabulate them in your table. The order in which you do them actually gives you a recipe for how to determine what the optimal solution actually was. The sequence of choices, as per the principle of optimality, how you made those choices. And that's how you get the actual optimal. So you construct, I'll say construct an optimal solution, because you can't claim that it's going to give us the optimal, because there might be several of them. Construct an optimal solution in a bottom-up fashion. So I'll often refer to this as the backtracing process. And I must stress that normally once you have number one, you can typically design recursive algorithms, and you can use memoization to speed them up so that they have the running time that you would expect actually from usually the dynamic programming algorithm. But when you use recursion, of course, it comes with the caveats of having the call stack, for example. So just be mindful of that. Sometimes it works in your benefit, sometimes it doesn't. We're going to focus on this whole bottom-up construction process, the dynamic programming at its heart. So there's kind of the theory of dynamic programming is the principle of optimality, but there's also the idea of just saying, hey, look, I could just use this recursive property to come up with an algorithm directly. Some people refer to that as dynamic programming as well. So like I said, if you ever run into somebody saying, we're going to use top-down dynamic programming, that's what they're referring to. They're referring to memoization, but they're using it in the context of dynamic programming. So what we're going to talk about here is bottom-up dynamic programming, or just what somebody might classically call dynamic programming. So we're going to do an example. So I must stress that number one, this is normally the hardest part. Once you figure out one, most of it follows through from there. So we're going to do an example. So this is going to be kind of like the big example we're going to do in class. I'll give you another example that I'm going to put in the notes for you to read. It's for the so-called longest common subsequence problem. It is actually a problem motivated in bioinformatics. So if you ever wonder, okay, how can I find two common strings such that so I want to find the longest common substring. You can actually do this with dynamic programming. There's a rather fast algorithm for doing this. So I'll include that in the notes. I want you to give it a read. But actually, I'll make a note of that right here, just so that you take note of this. So it's usually referred to as the LCS. I want you to just read that. I'll ask you a very basic question about it on the exam. Nothing too tough or anything. So we're going to look at the 0-on knapsack problem. So remember we talked about the 0-on knapsack problem before. Remember when I was putting my chocolate bars in the knapsack? So before, when we were studying greedy algorithms, we looked at the fractional knapsack problem. That's where I have an item. I can take a piece of the item, or I can take the whole of it, or I can take none of it. In the 0-on knapsack problem, remember, this means I have to take the entirety of an item or not. So it's either I take the item or I don't. So just as a reminder, so I'm just going to remind you of this because it's rather important for this problem. As I keep adding bad markers. This is terrible. I'm just going to chuck one of these. Here, let's go. Whoo! There we go. It's gone. Let's try a different one. This is going to be a marathon of me just chucking markers. Okay, reminder. So we either take an item or we don't. So remember here we have the knapsack capacity. So remember we have our items. Remember we have items. Pick so that we maximize the total profit. Such that the knapsack capacity W is respected. So this is also a questionable marker. It's gone too. It's gone. So let's try another one. It was this day. It was the day. So what are we going to do? So the first thing I want to tell you about is, remember how I said another lecture, a couple lectures back, I told you that the 0-on knapsack problem is a rather difficult problem. At least if we want to compute an optimal solution in polynomial time. So what I want to do is I want to try to take advantage of properties that the 0-on knapsack problem has to design a dynamic programming algorithm for it. But to find the markers, yes. So what's the first thing I have to do, everybody? What's the first thing? How do I know that I can even find a dynamic programming algorithm? What do I have to establish? So what's the thing I told you that I have to determine? It was that one thing. If I don't have this, I can't use this. I can't use this technique unless this is satisfied. I'll give you a hint. It's on the board and it's nasty. I need to use the principle of optimality, right? So I need to know that is a thing. So we will try to solve the 0-on knapsack problem. This one's even worse. Knapsack problem using dynamic programming. I'm going to grab another marker. Give me one moment. I'm just going to bolt it that direction. I'm going to grab another one. This one's going to. Bye-bye. I'm running. I'm on the marathon class. Give me a round of applause. I'm coming. I'm not even kidding. I am really running. I'm coming. I'm coming. There we go. I'm back. I'm back. Okay, here we go. Let's see if we can knock this out. So, we're going to be trying to prove that the principle of optimality applies. So that's the first thing we're going to do. So, oh, this is much better. Establish that poo applies. And then naturally we need to devise a recurrence. Because once we have those two ingredients, everything falls nicely in place. And like I said, you can use memoization and you can still build the table and so on if you want to do it that way. But I'm going to show you a very keen and clever way you could actually use, just like when I did the Fibonacci example, I can show you how you can compute an optimal knapsack using a table. But we're going to do that next class. What I'm going to do is I'm going to try to prove the principle of optimality for you for the 0-1 knapsack problem. Remember, this is the first place we have to start. And what's the great thing about this, and you might say, Dan, why do we have to prove this? Well, remember, the principle of optimality, like I said, it's a structural property of the problem. So it means I need to establish that it's true regardless of what problem instance I have. So let's prove a lovely theorem. And here's the neat part. This theorem's proof will give us the pattern we need to come up with our dynamic programming algorithm. So, theorem. The principle of optimality applies to the 0-1 knapsack problem. So let's prove this. Now, you might ask, Dan, how are you going to do this? You talked about this thing like overlapping subproblems and all these things. So how is this going to work? Now, the technique that's very common for proving the principle of optimality claims, sometimes people like to call it cut and paste. So the technique, some people like to call it cut and paste. And it's a loving name for this technique because that's effectively what the argument does. It's actually based on trying to yield a potentially better answer, but under the presumption that there exists a better one. So if I have a better one out there, and then I show you that, oh yeah, I can decompose my optimal solution into one that looks like the one that claims to be better, I can show you that actually my answer had to have been better, and it yields a nice result at the end of this, meaning there's a contradiction. So the proof technique, this proof technique very much aligns itself nicely with contradiction. So we're going to assume we are given an arbitrary 0-1 knapsack instance. So I'm going to just assume I'm just given an arbitrary instance. Suppose, now remember I encoded the solutions as an array or vector, however you would like to think of it. Suppose knapsack X, and I'm going to give it a tilde like this, just to indicate that it's an optimal one. It's just a symbol I gave it. X, X1 tilde, X2 tilde, all the way up to Xn tilde is optimal. So I'm going to suppose that this is indeed the case. So suppose I do have this. So I'm just going to give you some notation because I have to set up the proof because I have to make sure I have all this notation in place. Then once we do, the proof is dead simple. It's just a matter of writing it out carefully. So this means there is an optimal set of items, opt, which I'm going to refer to that as the optimal solution itself. So I'm looking at the set of items. So these are going to be the indices, or what the items will be. So it's going to be some subset of n items that we have, where xi tilde is equal to 1. That means I've taken this. So for each one of those, these are all the items I picked for the optimal knapsack. So I'm going to tell you that it has k items. So it's going to have k is equal to the cardinality of opt items, where k is less than or equal to n. So I'm just going to write out what the optimal profit would be. Then the optimal profit is the following. So I'm just going to write it out as a sum. So I have pi xi tilde from I is equal to 1 to n. So I just sum over all of I go across my array of all of these. I get all of the ones, so I just multiply it by each one of the profits of the items. And this is just going to be equal to each one of the items' profits. So this is just a set containing each one of the items, their indices. So I just sum up those particular items. So these two things are actually equal to each other. And so this is just a little bit of notation. And I can write out the knapsack's weight. So I sum over all of the weights, multiply them by each one of the values here, just like I did with the profits. Remember, we have weights for items. So I can do the exact same trick to just get a sum of all the weights. We know that this is at most capital W, the knapsack capacity, right? It has to be a feasible solution. So now I'm going to do the trick. Now watch this. So I'm going to proceed over here. So now I'm going to actually try proving this. So I have to do a little bit of setup, and I'm hoping you'll be able to give me a couple more minutes because I need to finish off this quickly. Because I'm just about to the end here. So I had to do a little bit of setup. Okay. So let item lambda be in the set opt. So it's going to be one of those items in an optimal solution. For the principle of optimality to hold, we need to show that for each lambda in opt, items opt where I remove lambda. So if I remove item lambda from the set of optimal items, it also has to be an optimal solution. Optimal solution, but it is to a very specific subinstance. To a subinstance with capacity W prime is equal to W minus the weight of lambda. So that means that there's going to be a subsequence of assignments. So I'm just going to give us kind of a briefer version of this. If you want the much more carefully explained version of this, just take a look in the notes. So just to write out just a little bit of more notation. So I'm going to suppose that there's a subsequence of assignments. So these are my selections. So I'm going to say I have x1 prime, x2 prime, x3 prime, all the way up to xk minus 1 prime. So if I remove lambda, that means that I have one less item in my optimal solution. So that's why it's k minus 1, not k. So now what I'm going to do is, so remember that lambda is not included. It's like batteries, you know, when you buy new toys. So I'm just going to call their profits and weights. So I'm just going to call their profits, the profits and weights for these selections. I'm going to call these P1 prime, P2 prime, and so on. And their weights W1 prime, W2 prime, and so on. This is just for sake of notation. You're going to see that a lot of this is just formulating it carefully. So now here's how it's going to go down. Now this is the copy in this cut and paste approach. So suppose opt without lambda is not an optimal solution. So suppose we know it's not an optimal solution. That means that there exists another assignment. That's the logical implication. So this means that there is another assignment. Another assignment y1, y2, all the way up to yk minus 1, which has larger profit. So I'm just going to give names for these as well. So I'm just going to call these, I'll call them PI double prime for the profits for each one of these selections. So they're going to be PI double prime for I is equal to 1 all the way up to k minus 1. Now, here's the trick. So can you give me one more minute, everybody? One more minute. I want to lay out the contradiction. I'm at the actual part where I do the contradiction. So I'm just going to set up the cut and paste for this. So let me just quickly do that. So I suppose that there's a better answer out there. So what I'm going to do is I'm going to decompose based on what I know. So I know that opt is an optimal solution, right? I know that is. My claim is that, so for the sake of the contradiction, I'm assuming that opt less lambda is not an optimal solution. So what I'm going to do is I'm going to imagine I take opt without lambda. I'm going to cut that out. I'm going to take what opt is. I'm going to plop back in what opt less lambda is, and we'll see what happens. So now the sum from I is equal to 1 to k minus 1, that's k minus 1, of pi prime xi prime is less than the sum from I is equal to 1 to k minus 1 of p double prime I yi. This is the assumption from our presumptions here. We said that those assignments lead to a one with a larger profit. These are just the names I gave the profits for their choices. So this is no different than me rewriting the following. What I'm going to do is I'm just going to paste in the profit that would be associated with lambda. So I'm just going to put that back in. So I end up with pi prime, xi prime. So my sum is equal to 1 to k minus 1. We're just going to add in back in the lambda item. Sorry, I have p lambda. So notice the indexing here. Like I said, most of this proof is just the notation. So I plop back in, so this is item lambda. I'm just putting this back in. So I'm just going to put that back in. Now here's how the paste is going to work. So remember this, I'm just going to put the right-hand side here. I'm just going to add also this same quantity. 1 k minus 1 p double prime I yi plus p lambda. In this case, it would be x lambda. I'm just adding this value to both sides of the inequality. But here's the thing. What's this? What's this right here? Well, I'll tell you. But this right here, that right there, is in fact equal to the sum over all of the items that are in the optimum without lambda. So if I sum over all of those, plus p lambda x lambda delta, right? Like, sorry, tilde. But this is, if I lump these two together, by definition, that's actually the value, this is actually the profit of an optimal solution. So this is the paste part I'm referring to. So I'm just pasting it together and I just slap it together. I just add back in the item that's missing and I, boom, there's the optimal solution. There's the optimal solution. So if I write down this, so if I sum over all of the optimal items, and I claim that I is equal to 1 to k minus 1 of pi double prime yi plus p lambda x lambda tilde. Is this true? Like, can this be true? Can it be true that the value of the optimal solution is less than whatever this thing is? Yes or no, everybody? So can this be worse than an optimal solution? The answer is this is an optimal solution. That can't exist, right? This presumption is just a bunch of bull. So, which is a contradiction. So if you want to see more of the details of this proof, just take a look in the notes. But this is the idea of the cut and paste technique. But notice that when I remove the lambda, all I do is I slap back in lambda without lambda in it, under my presumption, and all I do is I construct the optimal solution again, and I yield the contradiction. That's why we call it cut and paste. So anyways, that being said, when we come back, we're going to see how we use the principle of optimality to design our dynamic programming algorithm. I'll include the dynamic programming algorithm in the notes, so if you want to take a look a little ahead, we'll talk more about it on Tuesday. So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.